Welcome to clickmyproject.com. Let us discuss about relaxed min-max decoder architecture for non-binary low-density parity check codes. The AMC adaptive modulation and coding trend receivers select the most suitable coding and modulation mechanism subjected to the acquired channel information. Meanwhile, a control channel or a preamble is usually required to synchronously coordinate such changes between transmitters and receivers. On the other hand, low-density parity check (LDPC) codes become more and more popular in recent years due to their promising capacity approaching property. The broad range of variation in code rates and code word lengths for LDPC codes make them ideal candidates for future AMC transceivers. The blind encoder identification problem emerges when the underlying control channel is absent or the preamble is not allowed in AMC systems. It would be quite intriguing for one to build a blind encoder identification technique without spectrum efficiency sacrifice. Therefore, in this thesis, we investigate blind LDPC encoder identification for AMC systems. Specifically, we would like to tackle the blind identification of binary LDPC codes encoders for binary phase shift keying BPSK signals and non-binary LDPC codes for quadrature amplitude modulation signals. We propose a novel blind identification system which consists of three major components, namely expectation maximization (EM) estimator for unknown parameters, signal amplitude, noise variance, and phase offsets. Log likelihood ratio (LLR) estimator for syndrome, a posterior probabilities, and a maximum average LLR decoder. Monte Carlo simulation results demonstrate that our proposed blind LDPC encoder identification scheme is very promising over different signal to noise ratio conditions. In this paper, we propose optimized construction of quasi-cycle non-binary LDPC codes with moderate code length. This has a trellis architecture which will optimize the size of LDPC codes. The states can be grouped into clusters where all the clusters have the same number of states and all the states in the same cluster will be extended by the same branch matrix. A general solution to that problem, 4 orders of magnitude better reliability compared to conventional SEC-DED codes for typical soft error rates. Therefore, it is specifically helpful for memory severely affected by increased error rates in scaled technologies, either due to soft errors or errors occurring due to process variations. This is the overall flow of our project. This is a transmission and these blocks are in receiving side. The flow consists of 5 modules: arrange bits, check parity, detect error, correct error using ML algorithm, and recover output. In arrange bits, in this module we arrange the words which are needed to be error checking. These bits are arranged in bit by bit to shift register from this parallel bit to error checking method. The next block is check parity. In this model we find the parity bit as a value to find error bits. There are n divided by 4 number of XOR gates to get parity bit from parallel to shift register. These parity bits are considered as a parity word and fed this to majority logic circuits. The next block is detect error. In this model we check the error bit from the parity word. In this we first find the maximum likelihood bit range for neighboring bits. Then from this decoding using MLD algorithm. The next block is error corrector using ML algorithm. In this model we correct the error bit by checking last bit from shift register and bit from majority logic circuit. We apply the ML algorithm used to correct the error data and implement the process. In this error correction stage, we use XOR gate that changes error bit if there was change in bit. This compare bits from last bit from shift register and bit from majority logic circuit and finally correct error bit. The next block is recover output. In this model, we get error-free output from parallel to shift register. In this, if there was any error in the word, then it stops cycle checking and goes to next word. Since the error correction was done for single bit, we can correct error bit if there was a millions of error word. Open the source code folder and select main.m file. Right click on it and select run file. This is the throughput graph for the existing and our proposed algorithm. Compared to existing algorithm, the proposed algorithm achieves high throughput. And this is the bit rate plot for the different SNR values here displayed here for our proposed system. And this is the SNR plot, SNR versus SNR plot for different values 0 to 12 values. And this is a decoded bits here displayed in figure 5, time versus amplitude. And this is the transmission signal, and this transmitted wave, and this encoded signal. Figure 2 shows the encoded signal, the time versus amplitude. And here it displays the message input message signal displayed in figure 1. The throughput value is also displayed in a command window. Our proposed algorithm is high throughput than the existing algorithm. From this, I conclude that the fast decoding algorithm based on the fast Fourier transform reduces the computational complexity of the optimization algorithm significantly, and working in higher order fields are made computationally feasible. It is demonstrated by simulation that there is significant performance gain between the codes. This was made by providing a controlling mechanism in the stage of parity decoding. Output shows the performance of our proposed system. Thank you.